What's up, music nerds? Today we're reading chapter 11 of Hermann Helmholtz on the Sensations of Tone. The link to the webbook that I'm reading from is in the description. You can find the entire text of the book there, as well as all the apps that I'm going to share with you today. So let's get to it. Chapter 11, Beats Due to Combinational Tones. We looked at a few different kinds of combinational tones back in chapter 7. If you missed my video on chapter 7, check it out here. But for this chapter, we're going to be focusing on the differential tones, and for the most part, the differential tones of the first order. Now, for compound tones, we have to consider each partial a generating tone. So this table represents two compound tones, an incorrectly tuned fifth. That's pitch numbers 200 and 301. So here are the partials of the lower note, 200, 400, 600, 800, 1000, and the partials of the upper note, 301, 602, 903. And each of these pairs creates a combinational tone, which is the difference between the two pitch numbers. Now, if we take this whole table, all these pitch numbers, and rearrange them in pitch order, we get these groups of tones that are going to beat against each other. So the 97, 99, 101, 103 are close enough to each other that they're all going to create beats with one another. Same is true of 198, 200, 202, etc. Now imagine that this interval is correctly tuned. So instead of 301 up here, we have 300, 600, and 900. All of these would be 100, and all of these would be 200, 300, 400, etc. And there would be no beating of the combinational tones. So the first differential tone of compounds cannot generate beats except when the upper partials of the same compounds generate them, and the rapidity of the beats is the same in both cases. So if we look at the upper partials, 602 and 600, the upper partials are creating 2 beats a second. Now, the combinational tones 101 and 99 are also creating 2 beats in a second. Now, what about simple tones that have no upper partials? Let's take, for example, an out-of-tune octave. 2 simple tones, 100 vibrations in a second, and 201. The first differential tone is 101, and 101 is going to beat with the lower tone of 100. So a differential tone allows us to hear the beats of an out-of-tune octave, but for other intervals of simple tones, we have to move beyond the first order differential. For example, an out-of-tune fifth, 200 and 301. The first differential is 101, and that's too far apart from either of our generating tones to beat. But if we move on to the second order differential, which is the differential caused by the first order differential and one of the generating tones, in this case 200, we're going to get the second order differential 99, which will beat against the first order differential 101. For a fourth to beat, we have to get to the third order differential, and for a major third, we have to get all the way to this fourth order differential before we hear beating between 198 and 202. And Helmholtz concedes that that's pretty difficult to hear. So how do we tune simple tones like a stopped organ pipe or tuning forks? Well, we have to play a third note. First, we're going to consider compound tones consisting of the prime and its octave, such as the human voice when singing the obscure vowels of oo in two. We've got an out-of-tune fifth, 200 and 301, as well as their octaves, 400 and 602. And all of these intervals you can click to hear. So the differential tone for the lower notes is 101, and the differential tone for the octave is 99, which gives us 2 beats in a second. This same calculation for a fourth, 300 and 401, as well as their octaves, gives us 3 beats in a second. Next, we have compound tones consisting of the prime and the 12th. This would be stopped organ pipes, which have no even partials. Our numbers are different, but we still get to 2 beats in a second for that out of tune 5th, and same for the 4th. Now, compound tones having both octave and the 12th as audible partials. This would be wooden open organ pipes. For these tones, we can actually delimit a major third, a minor third, and a major sixth. So getting back to our simple tones, we can just add the tone that would be the upper partial. If we have an in-tune octave, 200 and 400, it's easy to hear an out-of-tune 5th at 301 because the differential tone with the upper note and the lower note are going to beat against each other. Now let's take this concept further. We have an in-tune 5th, 400 and 600, and we're putting an out-of-tune third between them at 501. Our 2 differential tones are going to give us 2 beats. We can tune a 6th with a 4th, and we can also tune a sub-minor third with a 4th. Now, at this point in the chapter, Helmholtz gets a bit, I'm going to say subjective. He's using his observations to decide which instruments are best suited for which aspects or genres of music. He starts with the wide stopped organ pipes, which produce very close to simple tones. He calls them unsuited to harmony because dissonance further apart than a second is imperceptible by beats, so they are used to produce softness and tunefulness. Next are flutes, which give us the prime and the octave, and sometimes even a 12th if they're loud enough. He calls them extraordinarily pleasant and attractive when played with other instruments that can affect the connection of the harmony. The principal stops of the organ pipe he calls quite favorable for polyphonic music. They have about 6 audible partials, which make the purity of consonant intervals and the disruption of dissonant intervals very easily noticed. The human voice is similar to the organ, but of course the vowel sounds have an impact on the force of the partials. For instance, a major third on an ah sound sounds more imperfect than on an o sound. And that's because of the 4th and 3rd partials, which are less audible in the o sound. Here's a fun little app. We get to hear See the Conquering Hero Comes on lu sounds, la sounds, and li sounds. I gotta leave you wanting more. If you want to hear See the Conquering Hero Comes on li sounds, you're gonna have to go to sensationsoftone.com for yourself. Next are bowed instruments, which he puts in first place for instrumental music because of their strong upper partials and expressiveness. Though he says they're not suited for soft, song-like melodies because of their piercing tones, or large chords because of the change in phase with every catch or scrape of the bow. But they're well adapted to quick figures and arpeggiated chords. Pianofortes he calls first place among plucked or struck string instruments, with lower notes having lots of partials and upper ones not quite as many. Brass instruments. He says The number and the force of their upper partial tones are far too great for the harmonious effect of the less perfect consonances, and the chords on these instruments are very noisy and harsh, so that they are only endurable in the open air. In artistic orchestral music, therefore, trumpets and trombones, which on account of their penetrative power cannot be dispensed with, are seldom employed for harmonies except for a few and, if possible, perfect consonances. I'm getting the sense that he doesn't like brass instruments very much. And finally, clarinets, which have no even partials. And so he says they can create pleasant harmony when played alongside a violin or an oboe to make up those unheard even partials. And that's the end of the chapter. I have a sneaking suspicion that modern musicians might not agree with some of these takes. So if that's you, write about it in the comments. I want to hear. And if you want to read anything in more detail, go to sensationsoftone.com and subscribe to the channel so you don't miss me next week with chapter 12, where we talk about chords. I'll see you then. Bye!